Back to my online classes. Let me start the next part of our online class. That is nothing but, in the last class we have already studied about the enzyme catalysis, isn't it? And in that we saw what is the meaning of enzyme catalysis, then examples we saw, then we saw the characteristics of enzyme catalysis, and today we will going to deal the next part of our topic, that is nothing but Michaelis-Menten equation. Okay, mechanism and the kinetics of enzyme catalyzer reaction. Mechanism and kinetics of enzyme catalyzer reaction. Okay, this Michaelis-Menten equation is nothing but mechanism and kinetics of enzyme catalyzed reaction. So here biochemist, I have already told about these enzymes which are there. We can also call it as an biocatalyst. So one of the biochemist, the name of biochemist, that L. Michaelis and M. Menten in the year 1913 proposed the mechanism for enzyme catalyzed reaction. Okay, propose the mechanism for enzyme catalyzed reaction. And this mechanism which will be there, which is having the following part or following characters, which are those mechanism as follows. Okay, in that first, enzyme molecules are having long chain and are coiled on each other to make a rigid colloidal particle with cavities on its surface. For what? For absorption of substrate, isn't it? So what is the enzymes? First, enzymes are the molecules or enzyme molecules are having long chain, having what? Having long chain and are coiled on each other to make rigid colloidal particle, with cavities on its surface, What I have told the first part, enzymes are the molecules having, these are having what? Like these long chains they are having, and the long chains which are there, they are coiled, means what? This long chain just like this, they are just coiled like this and on each other, and to make a rigid colloidal particle, it means it will make the rigid colloidal particles like this. Okay, and with cavities on its surface, they are having the cavities on its surface for what? For adsorption of substrate molecule. What I have told, the enzymes are the molecules having long chain and are coiled on each other to make a rigid colloidal particle with cavities on its surface. This is the first. Now second one. Okay, second one what? These cavities which are characteristic which are characteristic shape and bond in active groups like, which are active groups just like of NH2, COOH, SH, thio group, and OH, oxo group or hydroxo group, are termed active centers. Okay, so these are the cavities which are there. These are the characteristic shape and bond in active groups just like of what? NH2, COOH, SH, OH, NH2 amino group, COOH acidic group, SH thio group, OH hydroxy group, and are termed as active centers. These are what? Active centers itself. Means this cavity can be act as an what? Active centers. Okay, I will mention here what? The cavity can be act as an what? Active centers. Now the third sentence what they have told. In the first sentence what they are told, they are having long chain and they are coiled on each other to make a rigid colloidal particle, and they are having the cavities on its surface, and that cavities which are there, these are the characteristic shapes and bond in active group just like of NH2, COH and OH. These are termed as what? Active centers itself. And third what they are told, the molecule of substrate, the molecule, okay, in the third part what they have told, the molecules of substrate which have complementary shape fit into these cavities, just as what? Key fits into lock. Okay, just like of what? Key fits into lock. I will write in the bracket lock and key theory. Okay. By virtue of the presence of active groups, the enzyme forms an activated complex with the substrate which at once decomposes to yield the product. Means how the key can be engulfed or how the key can be adjust or fits into the lock. In the same way, the substrate molecule can be fit into what? Enzyme, and by virtue of the presence of active groups, the enzyme forms an activated complex, and we have already saw the activated complex, how it can be formed in the complex formation theory. Activated complex with the substrate which at once decomposes to yield the product, to yield the product. Okay. So the substrate molecule enters into the cavity, forms the complex, react, and at once product get out of the cavities itself. Okay. So what I want to tell you is that I have already told about these are the somewhat mechanisms of Michaelis-Menten equation. In that first I have told enzymes are the molecules which are having long chain and are coiled on each other to make a rigid colloidal particle with cavities on its surface. Now what I have told, the cavities which are on characteristic shape bond in active groups just like of NH2COH and SH and are formed the active centers, and the molecules of the substrates which are characteristics having shape and bond. Okay, shape and bond with what active groups just like of NH2COHSH, they form the active centers, and the molecules of the substrate which are having complementary shape means consider if this is the shape of your enzyme, the exact shape of your substrate molecule. Okay, complementary means what, how the key and lock with complementary with each other same way, fit into this cavity, just key that fits into the lock, isn't it? That is key lock theory. Then by virtue of the presence of active groups, the enzyme forms an activated complex with the substrate, and once it can be decomposed to yield what? Product itself. Okay. Thus, now what will happen? Thus, substrate molecule enters the cavities forms complex and reacts and at once product get out of the cavity and forms product, means at only one time they can be formed the product, isn't it? Just to see what I want to explain you is that consider this is our reactant, or we can also call it as in what? Substrate molecule. When this particular substrate reacts with what? Enzyme. Okay, enzyme site is like this. This is our enzyme. Now what will happen? How they will form the complex? Complex they will form, no doubt. So our complex is of like this. Okay, they will form what? This is the complex, isn't it? And now how the product will going to form? Again product will form, and again enzyme which will be there, it can be regenerated. This is our enzyme or remains as such, and this is our product. Okay, this is the principal feature of many enzyme catalyzed reactions we will going to deal now. Okay, this is about the Michaelis-Menten equation mechanism. Now next part what we will going to deal, the principal features of many enzyme catalyzed reaction. Enzyme catalyzed reaction. Okay, which are those? Just to see the principal features of enzyme catalyzed reaction. Just to see first one, for a given initial concentration of substrate, for a given initial concentration of substrate, I'll mention that particular substrate here. S, concentration of S, initial at means at 0 level. The initial rate of product formation, the initial rate of product formation, the initial rate of product formation is proportional to the total concentration of enzyme, is proportional to the total concentration of enzyme. Okay, I will write here concentration of enzyme E naught. What I want to tell you is that for a given initial concentration of substrate, initial at 0 concentration, okay, initial concentration of enzyme, the initial rate of product formation, how much product we are going to form at initial level, that is proportional to what the total concentration of enzyme. Okay, this is the first. What we are going to dealing here, principal features of enzyme catalyzer reaction. In that first I have told the given initial concentration of substrate, that is S naught, the rate of product formation is proportional to the total concentration of enzymes itself. Now second one, what I want to tell you is that second one is for a given concentration of enzyme, for a given initial concentration of enzyme, that is concentration, I'll write like this, and low values of substrate, low values of concentration of substrate, initial concentration of substrate, the rate of product formation is, the rate of product formation is, the rate of product formation is proportional to substrate, initial concentration of substrate. Means if for a given enzyme, how much amount of concentration of enzyme they have give, but low value of substrate is there, then what will happen, the rate of product formation is proportional to substrate, means initial concentration of substrate itself. This is second one. For first one, what I had told, initial concentration of substrate is there, initial rate of product also formed, and then it is proportional to the how much total concentration of enzyme. But second they have told, for a given total enzyme which will be there and low concentration of substrate is there, then rate of product formation is proportional to initial concentration of substrate. Now third one, what they have told, for a given concentration of enzyme, for a given concentration of enzyme or initial, the high value of substrate, the high value of, this is about the low value, the high value of substrate, okay, I will write here like this, high value of substrate, the rate of product formation become, the rate of product formation become, the rate of product formation become independent on, it is not depend on, independent on substrate, that is concentration of substrate, reaching the maximum velocity, reaching the maximum velocity, that is Vmax. Okay, what I want, for a given enzyme, the high value of substrate is there, then rate of product formation become independent of substrate and which can be reached the maximum velocity, that is V of max. How? Just see one graph, I'll plot and I'll show you. Just see, I'm plotting the graph over here. The x-axis can be indicates the substrate, substrate concentration, then y-axis which will be there, which indicates the rate of reaction, okay, and here Vmax, or it is like this. And what I have told, for a given E, that is for given enzyme, the high value of substrate, the high value means it just increases the rate, isn't it? Substrate, the high value of substrate, the rate of product formation, here the rate of reaction, product will going to form at high value, product formation becomes independent of substrate and reaching the maximum V, that is Vmax, velocity is maximum over here. They are told about the graph over here. Okay, this is third point. And the Michaelis-Menten mechanism, this is about the graph. The Michaelis-Menten mechanism, the Michaelis-Menten mechanism, the Michaelis-Menten mechanism account for these features, okay, account for these three features. Okay, first feature I have told, initial concentration of substrate, initial concentration of product formation proportional to the total concentration of enzyme. Second, I have told, given enzyme low value of substrate, the rate of product formation is proportional to the substrate. And in the third, if rate of substrate is high, product formation, high value of substrate is there for a given enzyme, then it is independent of substrate and reaching the Vmax. These are the three. Okay, so Michaelis-Menten mechanism account for these features, and according to this mechanism, according to these mechanisms, the enzyme combined with the reactant, that is substrate, to form enzyme substrate complex, giving a reversible reaction. According to this mechanism, I will write that point over here. I will finish this graph point here. I will write here, see. According to this mechanism, the enzyme that is E, okay, the enzyme E combined with reactant, that is S. I'll write here S. This is E, this is S. Right, reactant to form enzyme substrate complex, to form enzyme substrate complex, or may also call it as in what? ES. Okay, ES, giving reversible reaction, Okay, so how enzyme, it is just combined with substrate K1 first and K2 second path, they will form what? Complex. This is what? Enzyme substrate complex, ES complex, isn't it? Now the enzyme substrate complex so formed then decomposes to form the product P, and simultaneously the regeneration of enzyme. What will happen? The enzyme substrate complex, that is ES complex, second one, the enzyme substrate complex, that is ES complex, so formed then decomposes to form the product P, and simultaneously what will happen? Regeneration of enzyme, because it is already catalyst, we already know that, to form a product with simultaneous regeneration of the enzyme, that is, just to see how the reaction is going to possible. Yes, okay, path I will write, reaction path K3, product will going to form and enzyme can be regenerated, isn't it? Where in this 3, where K1, K2 and K3 are the constant. Okay, then we want to generate the equation right now, Michaelis-Menten equation or Michaelis-Menten equation. Just see, from the steady state approximation, I hope you understood these two parts. In the first part, the enzyme when combines with substrate, that is reactant, to form enzyme substrate complex, that is ES, and which is reversible, means both side it is possible, K1, K2, both are the reactant part. Second, the enzyme substrate complex, which is so formed, it is decomposed and then it will gives the product and regeneration of the enzyme, and where K1, K2, K3 are the what? Constant itself. And from the steady state approximation, from the steady state approximation, approximation ON, for the concentration of ES, we get, okay, what we will get, just to see, that is differentiation of ES, enzyme substrate complex, with respect to time, that is dt. Okay, so is equal to what? Rate of formation of ES from E and S. Rate of formation of ES from E and S, okay, minus rate of reaction of ES, minus rate of reaction of ES. Okay, so what I have told here, product from the steady state approximation, the concentration of ES, differentiation of ES with respect to time is equal to rate of formation of ES from E and ES minus rate of reaction of ES. Okay, then how we supposed to write this particular reaction? I will write, just to see, that is differentiation of ES with respect to time, that is we call it as dt, is equal to, I have already told, K1 is a constant, that is enzyme, and substrate ES, concentration of enzyme into concentration of substrate, minus K2 into ES, concentration of enzyme and substrate, minus K3 into concentration of ES, isn't it? That I have already told, rate of formation of ES from ES minus the rate of reaction of ES. But we have told, or we have took over there, steady state approximation, isn't it? So, but steady state approximation or steady state approximation condition hydrogenation condition, what it implies means, or what it tells means, condition implies that the rate of change of concentration, the rate of change of concentration of ES with time, with respect to time, it should be what? 0. Okay, then how in the equation implies d of ES divided by with respect to time, it's always what? 0. So rate of approximation, or the steady state condition implies that the rate of change of concentration of ES with respect to time is always be 0. So 0 is equal to, I'll take 0 sign this side, 0 is equal to K1 concentration of E into concentration of ES minus K2 into product of ES minus K3 into product of ES. Okay, now the next term, just taking the signs and minus signs this side, it will become plus sign. So what will happen, just to see, K2 into concentration of ES plus K3 into concentration of ES is equal to what? K1 into concentration of E into concentration of ES. Okay. So the next term, now E cannot be experimentally measured, isn't it? Means how much enzyme can be just took part in the reaction, we can't experimentally predict it. So now E, concentration of enzyme, cannot be experimentally measured. The equilibrium between, I'll tell this equation as a 1. Okay, I'll write this equation as a 1. So now E cannot be experimentally measured. The equilibrium between the free and bond which is found with ES given by the enzyme conversion equation. Free and bonded with substrate, isn't it? Bonded enzyme is given by enzyme conversion equation, is given by enzyme conversion equation. Okay, what I have told here. Now enzyme which cannot be experimentally measured, so equilibrium between the free and bonded enzyme which is there is given by enzyme conversion equation. So which is that concentration of enzyme at initial state is equal to concentration of enzyme plus concentration already bonded with substrate, isn't it? That is, free means first enzyme and bonded enzyme means bonded with substrate, isn't it? Where this E naught or E concentration of enzyme initial is the total enzyme concentration, is the total enzyme concentration. Okay, is the total enzyme concentration. So which can be measured, we can measure this. I'll write here, which can be measured. Next, simple E is there, is the free enzyme concentration, is the free enzyme concentration, free enzyme concentration. Okay, and ES which will be there is the bond or reacted enzyme concentration, bond or reacted enzyme concentration. Okay, reacted or bonded enzyme concentration. So the next equation is concentration of E, that is free enzyme, is equal to concentration of total enzyme minus concentration of enzyme substrate, that is bonded or reacted. Substituting, okay, substituting the value E, concentration of E, in equation 1, what we can write? We write equation 1. Let's see which is the equation 1. This is your equation 1. K2 E into S plus K3 E into S is equal to K1 E into S. I have already told about this equation, isn't it? So see, equation 1 we will substitute K2 concentration of substrate plus enzyme plus K3 concentration of enzyme into substrate is equal to K1 into E naught. We are substituting the value of E here, so E naught minus ES, enzyme substrate, okay, into S as it is. So now the next term we will substitute this particular brackets. What we will get, or we will multiply this bracket, what we will get, just to see, K2 ES as it is plus K3 ES as it is equal to K1 also as it is. We will get there E naught into concentration of ES minus K1 into ES into concentration of ES, isn't it? Now taking the same particles or same ES parts one side, what we will get, just to see, K1 ES plus K2 into concentration of ES plus K3 into concentration of ES is equal to K1 into E naught into ES. Okay, so the next term, the concentration, I'll write like this bracket, K1. Okay, so I'll took this ES as a common. Concentration of ES is equal to K1 into E naught into ES. Okay, so taking ES over here, enzyme substrate complex is equal to K1 into E naught into S divided by K1 into concentration of S plus K2 plus K3. Consider this is equation as number 2. Okay. Now the rate of formation of product is given by what? This is equation 2, we have already formed. Now the next part, the rate of formation of product is given by the rate of formation of product is given by the equation, that is differentiation of P with respect to time, that is dt, is equal to K3 into ES. So the rate of formation of product is given by concentration of product, that is differentiation of product with respect to time, is equal to K3 into ES. So substituting the value of ES from equation 2, what we will get? I will write here, substituting the value of ES. Substituting the value of ES, what we will get, just to see. Concentration of P divided by dt is equal to K3 into K1 concentration of enzyme, that is at initial level E0, into concentration of substrate divided by K1 into concentration of substrate plus K2 plus K3. Okay, so dividing numerator and denominator by K1, I will write here, dividing NR and DR, numerator and denominator, by K1, what we will get? Concentration of P divided by with respect to dt is equal to K3. K1 can be go because we have divided, into concentration of enzyme into substrate divided by K2 plus K3 divided by K1, okay, plus concentration of ES. So here, instead of writing K3 plus K2 plus K3 divided by K1, I'll take this is as an Km. Okay, so this part which will be there, instead of writing this all, I will consider this part as an Km. So what will going to form over here, just to see. So after considering as an Km, what will be the equation? dP divided with respect to time dt is equal to K3 into E0 into substrate divided by Km plus substrate. I have already told this is an equation number 4. Okay, this equation 4 is known as equation 4 is known as Michaelis-Menten equation. Okay, and the new constant Km is called Michaelis constant. Okay, and Km is given by what? K2 plus K3 divided by K1. Okay, I hope you understood this equation, which is very easy. Now, when all enzymes have reacted with the substrate at high concentration, the reaction will be going maximum rate, and the enzyme will remain so that E0 is equal to ES. And it is clear for every enzyme catalyzer reaction is found to be a first order, and the rate is proportional to the concentration of substrate. So always keep in your mind that every enzyme catalyzer reaction is first order reaction. Okay, the expression which will be indicates that the concentration of substrate is very high, the reaction becomes zero order and independent of the concentration. But what will happen? The rate of enzyme reaction is proportional to the enzyme concentration. So again, next part is there, bioenzyme and in its industrial applications. We will going to deal that in the next class. Okay. We start the next part of our topic, that is nothing but our next session of our topic. I have already told about the enzymes, and today we will going to deal about bioenzymes. Okay, bioenzymes. I have already told the enzymes which act as an biocatalyst. Bioenzymes and industrial application. Bioenzymes and industrial applications means how these particular enzymes applied in industrial sections. Okay, bioenzymes and its industrial applications. So in that, first, manufacture of ethanol from what? Starch itself. In that first part, manufacture of ethanol, manufacture of ethanol from starch. Just to see here how the manufacture of ethanol can be done from the starch itself. The enzyme, I'll write here only simply the name of enzyme which can be used here. The enzyme dietase, which can be present in germinated barley seeds. Okay, present in germinated barley seeds. Okay, it can be catalyzed, the conversion of starch into the maltose, means where the starch can be present, here starch can be present, and which can be converted into what? Maltose. Which enzyme can be used over here? Dietase enzyme can be used over here. Okay, so here first I will take starch 2C6H10O5 N plus N of H2O. The enzyme, I will write here dietase. Okay, and get converted into maltose, N of C12H22O11. This is your maltose, and this particular maltose undergoes hydrolysis in presence of enzyme maltase. I will write here maltose undergoes hydrolysis in presence of enzyme maltase. Okay, enzyme maltase we will get over here. Okay, in presence of an enzyme maltase or dietase, we will get here glucose. So I'll write here glucose 2C6H12O6. This is what? Glucose. Okay, now this particular glucose, the enzyme zymase present this particular glucose over here, the zymase enzyme which can be present in the yeast, which catalyze the conversion of glucose into ethanol. This glucose again catalyzed by the enzyme zymase. Okay, when in this glucose catalyze, the enzyme zymase present in what? It can be present in, I will write here, present in yeast, which can be do conversion of glucose into ethanol. This particular glucose C6H12O6, we will get here ethanol 2 of C2H5OH. Again 2 of C2H5OH ethanol plus 2 of CO2. Here also I can write 2 of CO2. If this 2 molecule you will take, you will get 2 molecules of this. Otherwise, if you took only 1 molecule, you will get only 1 molecule of ethanol. I hope you have understood the first that is manufacture of ethanol from starch. The enzyme which can be used over here, first dietase they will use, next they will use the maltose, and next enzyme they will use the zymase enzyme. And the starting product which they will do, they will germinated seeds, barley seeds, they are having what? Starch, C6H10O5N of H2O. Then dietase enzyme get converted into their maltose, C12H22O11, which undergo hydrolysis in presence of enzyme what? Maltase, and we will get conversion of their glucose. And again this glucose undergoes in the zymase enzymes which act on it, which can be present in the yeast, and we will get over here what? Ethanol, okay, or ethyl alcohol. This is our ethanol get formed over here. I hope you understood this particular application, manufacture of ethanol from starch. Now the next one, manufacture of ethanol itself, manufacture of ethanol from sucrose. Okay, manufacture of ethanol from sucrose. The enzyme invertase which is present in the yeast, I'll write the here is sucrose, I'll write C12, otherwise I'll first write here enzymes which can be used over here. The enzyme which is used over here, invertase, and another one enzyme they can be used over here, zymase. Okay, so in the first sucrose I'll take sucrose, first get converted into glucose and fructose, and then glucose get converted again by using the enzyme zymase into ethanol. So here C12H22O11, this is our sucrose. Okay, sucrose plus H2O in presence of an enzyme invertase. Okay, invertase, we will get over there glucose, C2H12O6 plus C6H12O6. This is your fructose and this is your glucose. Okay, so C6H12O6 also you can write over here, and this is your fructose, the C12H22O6 or H12O6. So now next part, this particular glucose C12H22O6 or C6H12O6, this is also your glucose itself. This glucose again undergoes the enzyme in presence of the enzyme zymase itself. In presence of enzyme zymase present in the yeast catalyst, glucose get converted into what? Ethanol. What they are going to form here? 2 of C6H5OH plus 2 of CO2. Okay, 2 of CO2 going to form. This is your ethanol. Isn't it? This is second application, which manufacture of ethanol from sucrose itself. The enzyme invertase and zymase can be used. The invertase enzyme present in the yeast and also zymase also present in the yeast. These two enzymes can be present where? In the yeast itself. The sucrose in the presence of enzyme invertase get converted into glucose and fructose. Again this glucose in presence of enzyme zymase get converted into what? Ethanol itself. This is second application. Now third process, manufacture of H2SO4 by chamber process. Okay, so 2 of SO2 plus O2 in presence of an catalyzed NO, nitrous oxide, gives rise to SO3. This is an example I have already told. This is one of the which type of example? Homogeneous catalysis, means both the reactant and catalyst which are present in the same phase. So manufacture of H2SO4 by chambers process itself. We have already saw this particular example in what? Homogeneous catalysis itself, where manufacture of H2SO4 by chambers process. 2 of SO2 gaseous phase, oxygen also in the gaseous phase and catalyst also in the gaseous phase. We will get there SO3 itself. Again by oxidation we will get SO4. So again various processes are there, but this is one example they have gave over here for this NO catalyst they have used here. Now fourth one is there, manufacture of NH3, that is manufacture of ammonia by Haber's process. Manufacture of NH3 by Haber's process. Okay, manufacture of ammonia by Haber's process. Again here N2 gaseous phase, again here H2 also present in the gaseous phase. This is one of the example of heterogeneous catalysis. Fe, which is present as a catalyst in the solid phase, we will get here what, 2 of NH3. This is one of the application, industrial application. Manufacture of H2SO4 by Chambers process, manufacture of NH3 by Haber's process itself. Okay, and then this is fourth one. Now next fifth one. Now the next one, fifth one, the hydrogenation of oil. When you do hydrogenation of oil in the manufacturing industry of oil, finely divided nickel is used as an what, catalyst. Then oil get converted into the fats. Oil plus H2, this nickel as an act as an what, catalyst over here. Now the next, in the manufacture of methanol, and ZNO is used as a catalyst and chromium cyclic as an promoter. So CO plus H2, ZNO can be used as a catalyst over here. And here we have completed our topic itself. Okay, if you have any doubts, please contact me. Thank you.